Hello everyone and welcome to yet another recreational programming session. I wanted to develop this specific feature for my programming language live on Twitch, but unfortunately Twitch chat was too distracting for me, so I decided to do that offline. I'm gonna start over because it's very important for me to document the development of that specific feature. So on the previous sessions we introduced variables and typed pointers, right? So let's actually take a look at them. Right, one of the things we introduced along with integers, untyped pointers, booleans and addresses, we introduced typed pointers, right? So essentially you can think of the signature, of the procedure signature as like a small sub-language that manipulates types, right? So if you say that, okay, the procedure accepts integer, you kind of push in a type onto the type stack, right? So by doing like double integers, you actually pushed two integers on the type stack and so on and so forth. Right, and we introduced a type constructor like pointer2, which takes the type on top of the type stack and turns it into a pointer to that specific type. Right, and you can actually do that several times, and every time you like add this constructor, it increments the pointer counter for that specific type. Right, so it kind of becomes like a small sub-language, right? The main language you program on the level of values, right? So you can push values 5, 6, like plus and so on and so forth. And in a signature, you push types describing what the procedure accepts and what it returns, right? So, and on top of that, we introduced variables, right? So they're like memories, but they are typed, right? So I can define something like x and say that it's going to be an integer, right? So, and let's take a look at how you can use that. So usually if you define a memory, y, you have to provide the size of the memory. Let's actually say 32, right? And you say, and you try to push that name onto the stack, you'll get untyped pointer to that specific memory. So if I try to compile that, so this is going to be Porth compile main.porth. You'll see that we have unhandled data on the stack, and that is just untyped pointer. But if you try to use x, which is a variable, you would have a typed pointer to that specific type. Right, so you see the type of the variable is an integer, but when you try to access that name, you're actually accessing the pointer to that specific type. And we introduced a couple of intrinsics that allow you to read the value from the pointer, right? So as you can see now, I dereference that pointer and I have an integer on top of the stack. And we also introduce exclamation mark, which saves a value into that specific variable, right? So it saves the value. As you can see, this thing consumes both of these values, right? So that's why this entire thing compiles. And it also type checks. It also makes sure that whatever you put in here is actually of the correct type. I cannot assign a boolean in here, right? So it will say that true is unknown because I didn't include the standard library, but that's besides the point. Right, so it will say that expected integer but got boolean, but you can easily fix that by turning this into a boolean. As you can see, just type checks and exclamation mark and add becomes sort of overloaded on the type of the pointer. Right, so this basically forms the system for variables. Okay, but the problem with variables is that we can only have primitive types in here and the pointers. And I would like to have some sort of like a mechanism for defining bigger types for variables. And today specifically we're going to implement structures, right? So structures are going to be a way to group together several primitive types and other structures, right? So we're going to introduce a struct keyword, and then you'll be able to define like a sequence of primitive types and other structures that form this specific structure, right? In case of the string, I want to have the counter, basically the size of the string, and the pointer, which points at the beginning of the characters that represent the string. Right, and I want to be able to actually define variables of that specific type. For example, I might want to define a variable name, which is a string. Right. And of course, the size of the structure is actually 2 words. So this entire thing is going to be bigger than just a single word. Right. And how do I expect you to access the this specific structure? Well, if you try to put a name in here, you're supposed to have a type str pointer to, as usual. Right, and I want to introduce another second keyword which allows you to sort of offset the pointer to the beginning of the structure to a specific field. Right, so that keyword is going to be colon. Right, it's going to be colon. Right, as you can see, we have two fields in here, and for now, I want to access them by their numbers. So this is going to be the zeroth field. This one is going to be the first field. And if we're going to add, this is really weird. If we're going to add more fields, it's going to be numbered accordingly. So they're going to be like zero index based. So, and by doing something like this, you basically turn the pointer to a string to a pointer to an integer, right? To a pointer to an integer, which you then can dereference and like read the actual size, or you can update it like so. And of course, without the comments, it should actually look a little bit better, right? So if I just do it like that, it will look like this. So this is how you assign the size of this thing, and this is how you read the size of the string. So this is how it's going to look like. And of course, accessing fields by their numbers is not particularly convenient, so I'm going to use in the future the same keyword for assigning names to the fields of the structure, right? So I have a field integer, right? I'm going to say, okay, assign the name count to that specific field. And if I have a pointer, I will say assign name date to that specific field, and that way you'll be able to say, okay, name count, let's set the count of the name to 32, and then let's read this entire thing and print it. Right, so essentially keyword colon is going to be immediate, right? So that means it will look at what's ahead of it, right? And also it knows what's behind it. It knows the type of the structure, right? And then knowing the type of the structure and knowing the name of the field that we want to access, it will basically overload and produce the correct offset for that specific field. Right, so this is how I expect all of these to work. And since we also have this sort of like a mini type language within the structure, you can have like pointer to an integer and like pointer to a pointer, right? And in the context of this type definition, the colon keyword might basically act like an assignment of a name to a field that is on top of the type stack, which means that you can probably have several names, right? So maybe I'll have not only count but size, right? And that will mean that you have like several names for that specific field. But all of that is in the future, right? So this feature is not implemented yet. I'm just like, you know, fantasizing about what's going to be. So for now, I want to implement access to the fields just by an index, right? Because this is the easiest thing to implement, right? And then once we have that, we can introduce the names, and once we have that, we can introduce several names, and so on and so forth, right? So, and that's basically the design of this feature, and let's just go ahead and implement it. All right, I've been talking too much, so let me make a small break, like a quick break, and we're gonna go ahead and just start implementing that feature within the current code base. All right, so let's go ahead and implement that, shall we? So we're gonna start with probably parsing the structures, right? And also maybe we want to define the structure for the structure, so if that makes any sense. So essentially, we need to store the definitions of the structure somewhere, right? And for that, we're gonna define a structure, hopefully. Hopefully. I don't know what I'm talking about, I'm sorry. So we're gonna have a struct, and the structure usually has what? It has a name, right? And it's gonna be size of a string, right? So here's the name. So the second thing we wanna do is to probably store the location of the definition. Like all of the constructions in a language, they usually know where they're located, so we can use that in diagnostic messages, right? So this is gonna be struct location size of loc, and there we go. And the next thing is a sequence of types, right? So originally I wanted to use the type stack, right? So basically we're gonna have types, and this is gonna be size of type stack, and type stack is a construction that is used during the type checking process and stuff like that. And I think that is not particularly suitable because we also will need to associate names with the types of the structure. So it may not easily work like that. So what I'm thinking is that maybe we're gonna have something like fields, right? So we can define another structure called field. And the field is going to have a type, a specific type that is assigned to field. And in the future, it's probably going to have some sort of a name as well, but not necessarily. Right, so I'm going to just like create a name just in case, but I'm not going to use it for now. And let's finish the definition with the size of the field. So this is going to be reset, and I forgot to put offsets in here, so this is going to be an offset. Nice. And here we're going to have fields, right? And fields is essentially going to be a pointer to the beginning of the array of the fields, right? And then we're going to have the size of that array somewhere, right? So we're going to have fields count, which is size of an integer. Right, and this is basically the entire structure for the structure, if that makes any sense. And yet again, I forgot to put offsets at the end in here. Right, so this is going to be an offset. Might as well align everything by the size, so it looks a little bit nice. I don't know if that makes any sense. Okay, and how are we going to like maintain these sort of like variable length arrays? I think we're going to have a pool of fields, right? So let's define fields capacity, and let's say we're going to have like 1,000, like 1,024 of them. It's just like arbitrary number. And let's allocate some memory for the fields, right? So this is going to be fields, size of the field, not file, but field. And maybe it makes sense to actually define it like right below the field definition. And we're gonna take the capacity of the fields array and multiply by the size of the field. And there we go. So we defined an array of the fields, and let's define the amount of such fields in that sort of pool. Right, so it's gonna be an integer like so. And the idea is the following, right? So imagine that we have a pool, and we're starting to parse the struct definition. Right, so we have fields. And as we parse the struct definition, right, so it's going to be integer and then the pointer, right. So we're pushing the fields into the global fields array, right? So it's going to be integer, pointer, and before we start pushing, we remember where, like, we start pushing, where is the beginning of that array. And as we reach the end of the definition, we also know how many elements we pushed so far. Right, and we can basically assign that information, the beginning of the fields array and the amount of the fields, to these two, fields of the structure definition. Right, so this could be the fields of the str. Then we can define something like location, right, which is going to be essentially pointer for the file path, multi-terminated file path, then the row and the column, right, and all of that is going to be appended in here, pointer, integer, integer, and this is where we sort of start the fields of the location thing, right? So essentially all of the fields of all of the structure definitions are going to be put into a single array. And then within the structure definition themselves, we're going to have a pointer to the beginning of the field array and how many fields we have to sort of like consider part of the structure definition. So that's going to be the idea. As we parse everything, we just like append all of the fields in here. I think it's going to be a better approach, because then you would be able to associate as many different things with the fields as you want without like patching up the mechanism that is intended for type checking, rather than holding the definition of the structure. So I think it makes a little bit more sense. Though if we're gonna go the route of several names per field, I'm not sure how we're gonna implement that yet, right? So because this kind of approach supports only one name per field, and to be fair, several names per field is not really that important if it's not gonna be technically easy to just slap on, I don't think it's going to be that much of a problem to just not have that. Or maybe once the language is more mature enough, we're going to have more sophisticated ways of managing the memory, so it will be easy to implement that in the future. But having more sophisticated ways of managing the memory requires more powerful type system, which we are in the middle of implementing. So yeah, so we just need to like implement something that is better than what we have right now, so we can use to implement it even better system, which can be used to implement even better system, and so on and so forth. It's sort of like a self-perpetuation process. So if something is not really easy right now, we should just not implement it until it becomes easy, right? If you know what I mean. So we're gonna go this route. And let's see. So this is the fields, this is the amount of fields, and of course we need a global array of the structures, right? So let's do const struct capacity, and let's say we're gonna have 1,000 of the structs, because why not? So we're gonna allocate the memory for the structs, structs size of a struct multiplied by the struct capacity. Right, struct capacity, and then we're gonna have structs count, integer, and there you go. So we've got this going for us, which is cool. Now, we probably want to have two usual things for the structure definitions, as we have for variables, memories, procedures, and stuff like that. Essentially, a procedure that appends the structure definition to the array, so we can do something like struct define, which accepts a pointer to the structure and then just copies that and appends to the global array of structures. So we're not gonna implement it right now, so it's gonna be to do. Struct define is not implemented yet, right? It is not implemented yet. And another thing we usually have is a struct lookup, right? So which accepts the name of the structure, right? So it's an integer and pointer, and should return a pointer to the structure definition, or null if it's not found, right? So here we can do swap drop, and then to do struct lookup is not implemented yet. There we go. So let's see if this entire thing even compiles, because who knows, maybe it doesn't. So this is going to be Porth. All right, so it seems to be compiling. So let's start with like trying to maybe compile this current code, right? So we already have a simple example, right? So we can try to compile that example and keep modifying the compiler until it compiles. So that makes sense. So maybe for that specific process, I'm going to use the Bootstrap compiler. Then I'm going to recompile the compiler with the new features, and then I'm going to try to compile the this example. And as you can see, words are not allowed at the top level, and this is because the compiler does not consider sequence of characters struct as a keyword, so it thinks it's a word, and words at the top level are not allowed, right? So let's go ahead and just introduce a new keyword, right? So let's go into the Lexa and find the keywords. Here are the keywords, and let's just go ahead and implement that. So the keyword is going to be struct, right? So this is a struct keyword, and let's follow the compilation errors. So here we need to introduce like a conversion between names and whatnot. So if we encounter struct, this is a struct keyword. Another one is, it's probably for logging, right? So this is going to be struct, and this is going to be struct. It's the other way around. All right, so now this is, as far as I know, this is the compile time evaluation. So we're probably not going to support structure definition in compiled in const evaluation. So I'm just going to increment and move on. So this is the actual compilation, and we probably need to put something in there. All right, so let's find the place where we can put the compilation. So we have memories, right? So I can see some memories, but maybe it's not a good idea to put it there. Okay, so we have return, we have a cast, and let's introduce keyword struct. And in here, I'm going to just put it to do. Compilation of struct definitions is not implemented yet. It is not implemented yet. So I'm not sure if I need to drop anything in here, probably not. Okay, and as you can see, we instantly hit this thing, and we can even see where exactly we stopped. So let's do located here, right? Located here, and we stopped exactly at struct in here, so everything seems to be fine. Cool. And what we need to do, we just need to parse the name of the structure. What's interesting is that we have a lot of repetitive code which does the same thing essentially. Right, we have some sort of a keyword that defines the beginning of some sort of definition, and then the name of that definition. Right, so we have struct and the name of the structure, variable and the name of the variable, procedure and the name of the procedure. We also probably have memory and the name of the memory. So, and for all of these sort of like definitions, we have the same code that looks into the next character and next token and checks whether that token is word or not. And it's kind of tedious to repeat that code over and over again. So I think I want to extract all of that into a separate procedure that basically parses the name of the definition, right? So you basically only need to parse the first keyword and then ask parse the name of the definition, and it will check if there is the name, whether the name is a word or not, and then it will just return you the name that it managed to parse, right? So I think that's a pretty good approach, and let's go ahead and implement that. So I'm gonna go to proc, and in here we're gonna do something like parse name of definition, right? And here we're gonna accept the pointer to Alexa, right? And this entire thing is supposed to return the string, right? And let me see, str. So to do parse name of definition is not implemented yet. There we go. All right, compilation of struct is not defined, so it's the same thing. And the first thing I want to do essentially is just Alexa, Alexa, parse name of definition, right? And that is supposed to return the name, which we can probably print, something like puts. So struct name, eputs, and then the new line eputs. And then we're gonna align everything like so. Okay. So, and something went wrong. Oh, I see what went wrong essentially, because we asserted in the middle of printing a message, so it's sort of like printed the location, right, like in the middle of the message. That's fine. Okay, so let's actually find the keyword memory. I don't know, keyword memory, and this is what we do to get the name of the definition, right? So first we try to see if we have a token at all, then we see what kind of token is that a word or is it something else, and then we extract that word and use it as a name. So this is basically a code that is repeated throughout all of the definition parsing, and I probably want to just like extract that into a separate procedure, right? Parse name of definition. So I'm gonna put it in here. So here we have Alexa, and I'm gonna just put let. So this is the Alexa, and then let's allocate a little bit of memory for the token, size of token, and this is the end. So in here it's gonna be an end. So this is let. So, and this is the end. Cool. So I probably didn't want to do it like that, but let me quickly do it like this. All right, so Alexa token, expected name but found nothing, expected name to be a word. So, and both of these things I think has to be errors. All right, so it's going to be error. Let me also do align eput and align eput. Cool. So after that, after we confirm that everything is correct and we have a word and we have a name, we should just return the value, which is going to interpret it as a string, and that should be basically it, right? That should be basically it. Unknown word lock, and location I think location is from the token, so it's a token lock pointer plus. Right, so what else do we have in here? So, and yeah, I had a lot of bindings for those things. Token type pointer plus, and that should be more than enough. Still lock. I might have as well just like created those bindings super quickly, because why not? It's just like it doesn't really cost me that much. So this is going to be token type pointer plus. Right, there we go. Here's the type. Might as well read it. And then token location pointer plus. So this is the location. And then token, what was that? Value pointer plus. I can just go ahead and take a value and read it as a string. Would that be enough? Hopefully. Value. I forgot to bind the value. What else do we have in here? Type is already red, so it's not needed. Cool. Expect your name to be a word, but found assertion. That's very interesting. So while trying to print a structure name, we got an error, and during printing an error, we got an assertion with unreachable, which is rather interesting. Expecting word to be found. Something is very, very wrong, and I'm not sure what exactly. So, okay, so this is the Lexus. So we have type, and we read the type, then the location, then the value. So I suppose, oh shit, we should not try to read the type before we actually read the token, right? Because that sort of solidifies the type. We should keep type a pointer, right? Okay. So let's just keep it like that. Otherwise, it just like doesn't make any sense. That's cool. I'm really glad that I put a lot of assertions, and they actually saved me from a lot of bad situations. So assertions are really important. There we go. So we have a struct name str, right? So here is the str, and then we have this problem with the compilation. So I'm thinking that I'm gonna just go through all of these things and use that parse name of definition for like all of these things. So let's take a look at what we have. We have an assertion. Assertion kind of similar, but it actually expects the string. So, and assertion is only one such thing, so I don't think I'm going to apply this thing for assertion, but maybe in the future we'll be able to. Okay, so here we have check name redefinition, right? Check name redefinition. And then we just reuse it several times in here, which makes it not particularly pleasant to reuse, unfortunately. I really don't like the fact that it just like reuses this name, but okay. For the memory, it is like that. So then it is really not particularly easy to just like go ahead and start refactoring all of these definitions, unfortunately. So I think I'm going to basically just do that off screen, because it's actually too much work, right? So because I need to like restructure all of this code right now, and it's kind of besides the point of what I'm trying to implement right now. Anyway, so let's continue. I thought it's going to be like a quick refactoring, but apparently it will just take some time to do that. So we've got the structure name, and the next thing we need to do, we need to parse the structure definition, the structure fields. So let me go ahead and allocate enough space for a structure, right? So here we're gonna have a struct. So I usually just call this variable struct, but it kind of messes with my brain, so I think I'm gonna do something like struct t. Right, so yeah, because it's just super easy to just add extra t and without like screwing up with my brain too much. And the reason we can't use struct is because it's a keyword, right? So we can't use that name, unfortunately. I was also thinking to introduce maybe some sort of a syntax that allows you to put you know, keywords in backticks, and that will be always interpreted as a word regardless of what it actually is. So that's not a bad idea, actually. I'll think about that. I'll think about that feature. So it should be pretty easy to implement. Just reuse the lexing code for strings, but do that with different quotes and just put a different type instead of like string literal. So I think that's not bad. Anyway, so this is going to be struct. Right, and in here we're going to have struct name pointer plus. Then I take the lexa. Right, I take the lexa and I just save the string in there. There we go. So we basically parsed the name of the structure. The next thing we want to do is to probably parse struct fields. And this one is rather interesting because I want this thing to return two things: the size of the array that we parsed, the array of the fields, and the pointer to the beginning of the array. So that way we'll be able to do something like struct fields count pointer plus, save it as an integer, and then fields save it as a pointer. Right, so something like this. So we'll be able to save these two things simultaneously. So we have a name, we have fields, and the other thing that we have not yet put in there is probably the location. Right, so let me quickly do that. The location is going to be, right, size of location, then the location, then the location, then the destination is going to be struct lock pointer plus, and then we do memcopy drop, right? Emacs, what the hell is going on? Right. So yeah, I don't know how to organize all of that. Okay, so it looks fine. It looks fine. So yeah, location, name, fields, and that is basically its size of struct. Yeah, I think I got everything covered. Right, so this is the definition, and after that I can go ahead and say struct define. Right, we're defining the structure, and that should be essentially it. Let's try to compile the entire thing. Right. Parse struct fields. So here we're gonna accept the lexa. It should be actually something like this. So the lexa, and then we're gonna return integer and the pointer, and in here what we're gonna do is probably I don't know, it's gonna be drop, and then we can just provide a string, which is not particularly correct, but it's just something to type check. Parse struct fields is not implemented yet. Right, it is not implemented yet. Cool. So what do we have in here? What kind of problems do we have in here? So int is expected integer but got pointer, so it was provided in here. That is not particularly correct. So that means I have to swap these things around. Okay, that makes sense, I think. Insufficient data on the stack, expected pointer. Excuse me? We have to provide something? I'm not sure if we have to provide anything. So it feels like maybe we have like extra data in here. Let me see. Stopping the compilation. We don't have any extra data, but are we supposed to have any data there? I'm actually not sure. Not sure at all. I don't see any problems, honestly. So struct define. Right, it just accepts the pointer. We don't have any data in here. And then it says that we have insufficient data on the stack and expected a pointer at the compile. Man, what the hell is going on? TMP alloc. Because whatever is returned in here is consumed in here, so I'm really not sure what it wants from me. So if I try to do something like this, like I should not have anything. Okay, so I've got the pointer. Alright, so this is the pointer. Okay, so the pointer is here. And the pointer... Okay, so looks like something consumes. Alright, parse struct fields does not really return two things. Is that what's going on? Because here we have a pointer that is put in here. Okay, so that makes sense. And then after this thing, pointer is provided in here, an integer. Oh, I see what's going on. Holy shit. A parse struct field is supposed to take a pointer to the lexer, but since I didn't provide the pointer to the lexer, it consumed something above. Man, I'm so glad that they implemented this question mark thingy. It's actually very, very useful to like investigate this kind of stuff. But the type system should be powerful now. This should never happen, right? So in the future, when we have the pointers to the structure, this procedure should accept pointer to Alexa, and whatever we had on the stack back there should not be compatible. So it should be immediately obvious that we didn't provide the pointer to the Alexa, right? So the only reason why this happens is because we have a very weak type system, but we are in the middle of making the type system more like stronger, right? So that's why we have to sort of get through that phase of programming in a language that is like weakly type and making it stronger and stronger. So that's totally fine. So this kind of stuff should not discourage us from implementing the things, because that's the reason we are implementing those things, to actually get rid of such problems in the future. See what I'm talking about? Right. So it's very important to, you know, constantly encourage yourself when you encounter something like that, and don't get discouraged. Just don't get discouraged. Just don't get discouraged. All right. So I've been talking for too much, so let me actually make a quick break, and we continue developing the rest of the procedures that are not implemented. All right, so let's go ahead and implement this specific function, but maybe not this one, maybe the one that the compilation process will complain about. And that's the function that compilation process is complaining about, so everything's fine. All right, so we're going to be starting to use the fields, global fields array as some sort of like a type stack. Right, so that means we need to have something like fields end, right? So that will push a pointer at the current end of the fields, and we'll need to be able to append new types in there, but we'll see how it goes. So we're gonna start the process of pulling the tokens from the Alexa, right? So that means we also need to allocate the memory, token size of token, there we go. And here we're going to do the following thing. If Alexa next token, we have to provide the token and we have to provide the Alexa. But with Alexa, we have to maybe, you know, bind it. So it's a little bit easier to use, just a tiny bit easier to use. So here's the fields. And then the token, and if it's not available, right, so this should never be a reachable state, right? So if something like this happens, that means the file has ended before the structure definition was finished, so we'll have to say something about that. All right, in that specific case, we'll have to do allocation. So I think I'm gonna just like do token location pointer plus, right? And that's the location of the token. So I can always do. Oh yeah, if the Alexa next token returned false, that means the token was not modified. So we'll have to directly take the location from the Alexa. I think it's get lock, right? So we'll have to provide the location, the Alexa. Then the Alexa get location, that gives us the location, and then we can do put lock error end of reached end of file before the end of the struct definition or something like that. It's just like something. And we're gonna exit with non-zero exit code essentially. So that should be it. After that, we do have something in the token, and the only thing we care about is words and keywords. If we encounter something else, we will not allow that for now. So maybe I'm gonna also do token type, right? So this is gonna be point plus. And in here, we're going to do type, integer, and the types we care about is the token word, right? And the token keyword equal to that, and everything else is not implemented, right? So to do parsing parsing words is not implemented yet. And here to do parsing keywords is not implemented yet. Here we just right away say that we do not support this kind of words. Also, I would like to have put located here. I think it's going to be useful. So in here we're going to say input log error. Inputs. Oh, I think I know what I'm gonna say. So this is the type, right? And I'm gonna do the human plural, I think, right? So token human token type. So essentially what it does, it takes the token type and turns it into a human readable string, right? So if the type was integer, it will say integer, but if you provide like plural, it will say integers, which is exactly what we want. So we can say like integers are not allowed, are not supported in struct definitions, right? In struct definitions, and even the inputs one exit. There we go. So this is going to be a line input. All right, so integers are not supported in struct definitions, so everything's fine. We can even try to test all of that. Right, so if I try to do that, fields end. We don't have fields end, unfortunately, so let's go ahead and implement that thing. So where do we have fields? Here they are. So this is going to be a procedure that simply returns the pointer, and the pointer is essentially fields, but offset by fields count. Right, and we're going to multiply it by the size of fields, right? So multiply by size of fields, and then we offset by that. And we can also make it unlineable, right? So it doesn't, like, you know, perform any actual call. It just like inlines the entire body in here. Because it's a very small function, because why not? So it's better to inline small functions like this. Okay. So the type, and the type is not available, and this is because I never actually bound the type, so let's quickly bound that. So plus, this has to be pointer plus, I think, I'm pretty sure. Do expects a boolean, so this is something that we'll have to do in here. So this is false, and in here it's going to be true, true for now. All right, so insufficient data. On the stack integers. So, oh yeah, so now we need to like push an integer of some sort. So after the entire loop is done, what do we have on top of the stack? Let's find out. So it should be just a pointer of the field, right? So yeah, so we push the field, so here it is. What we can do, we can duplicate this entire thing, right? So let's duplicate that. So now we have two pointers. And then let's take TMP end, not TMP but and fields end, right? So this is the fields end, and we can swap them. So the end of the fields goes first, and we can basically find the difference between these two pointers, right? So which gives us an integer, which we can then divide by the size of the field, which gives us the size, the amount of you know, elements we put in there. So that should work. So it's an integer and a pointer, but we expect, I think we expect them in a slightly different order. So let me try to put it like that, and it will say that, yeah, the order is kind of fucked up. So let's do a swap. Right, and that way the order is going to be fine. Parsing words is not implemented, so we're already getting somewhere. As you can see, it encountered the word and said that it's not implemented yet. So, okay, if I try to put something else in here, like 69, it should say that integers are not supported in the struct definitions. Yeah, that's precisely what I want you to see. We can even put strings, right? And it will say strings are not supported in the type definition. So, we only care about the words right now. So, though, maybe I want to start with something more simple, maybe not, I'm not even sure, we'll see, we'll see. Okay, so we encountered the word, and now we can try to parse the word as the type, right? So as far as I know, we have data type by name, so we can take a value, read it as a string, and this is data type by name. It should return integer and boolean, basically type and a boolean. We don't have a value, really? Okay, we can just do that like this. And here is the boolean. Okay, if this is not parsable, right, this is not parsable, we should throw some sort of error. input lock error, we can say something like value, it's not a string, it's str, is not a type, right? So this thing is not a type, and we're gonna exit with non-zero exit code. There we go. So we're gonna align input like so, and unexpected data on the stack. So this is the okay. So and then we've got an integer that we'll have to consume in here. So okay, how are we gonna consume all of that? We can try to just field push type. I think that's a very good idea, right? So essentially it will just push a new type into the global field array. I think it's a good idea, right? And of course it's not implemented. Let's go ahead and implement it super quick. So it will accept a type and it's not going to return anything. So in here we'll have to do something special, all right, first of all, we probably need to check that we don't overflow the fields thingy, right? So fields count, we're gonna read that, and if it's greater or equal to the capacity that we have, fields capacity, so greater or equal, we'll have to do something like this. Assertion failed, fields overflow, right? So that's what we have. So now we are sure that we're not going to have a fields overflow. Fields count at, no, we can just do fields end, I presume. So this is a fields end, and now what we can do, we can clean it up, I suppose. Right, we can try size of field over. I'm not even sure is like how memset works. I forgot the let's think memset. So size, then the byte, and then that thing. So I'll have to do something like dupe size 0 and then rotate, and that will give me the memset I want, though it will be just easier to do something like this, right? Size of field 0 top memset, so that cleans it up just in case, right? That cleans it up just in case. Then we're going to take the type, right? So we've got the type, so it maybe also makes sense to, yeah, type and the field. All right, so that makes a lot of sense. Cool. Type and the field. Though I just realized I do have a special procedure, I think. I'm pretty sure I have a special procedure in the standard library, std Porth, called Append Item. Right, and it basically appends an item to a fixed array and does all of the checks for you. Like it checks for overflow, and it doesn't really do that much. It's just like copy-paste stuff. So we can try to do that. Probably. Is that a good idea? Maybe. Right, so for that we're gonna do memory field, size of field, and we'll have to clean it up anyway, right? So we'll have to do size of field, 0 field memset drop, right? Then we're going to do field type pointer plus, and we're gonna just save that type. And after that, we can try to use append thingy-majingy, right? So item size is size of field, then the item itself is going to be field, array capacity is fields capacity, the array itself is fields, and the counter is the fields count. There we go. And then we say append item. And if all of that did not work out, we can just say that this entire thing overflew. Right, and then we'll have to drop the index that is returned by append item. We might as well also just like merge all that together, it doesn't really matter. Right, so that's basically what we can do in here. Not sure of how useful that procedure is, but it does things, I suppose. Okay, so it pushed the type, and that's pretty cool. So I think we can try to remove that. So if Data type by name didn't work out. I think we have to do stuff slightly differently. Right, so we got that. So this is else, and I can move field push type in here. Otherwise, we can check if the value is equal to pointer2. Right, if it is equal to pointer2, we'll have to think what to do. Str equal. Right, let me try to do that. So I think I'm gonna drop the entire thing anyway. Though we can try to drop that thing in here, right? So yeah, that makes sense. And then this is gonna be to do parsing pointer2 in struct definition is not implemented yet, right? So it's gonna be that. Right, and that should be basically it, right? So this is a primitive type, then not so primitive type, and then not a type at all, and we always continue the execution like so. All right, so else can only come, yeah, I suppose here I forgot to put a star, pretty much. All right, so it means that it parsed everything. So if I add like pointer2 in here, it's not going to work, right? But I don't think it's that important anyway, right? So parsing of this thing is not implemented. So let's not support that for now yet. I can always add that support like off screen. So what's important right now is just to have like the basic feature working. So for the keywords, we're looking specifically for the AND keyword. We're not going to support any other keywords right now, though we'll need to support the colon at some point. So, but the colon is not a keyword right now. So this is a value. We're going to read the value as an integer, and if it is equal to keyword AND, right, essentially what we're doing, we're just like quitting the entire thing. If it's something else, we're going to say that this keyword is not supported, right? So lock input lock, right, then error, keyword eputs value.int keyword name, I think, yeah, keyword name eputs is not supported in struct definitions eputs one exit, and let's align eput like so. Cool. So, and of course this entire thing is going to be false, and since both of the branches are kind of false, maybe now let's actually keep them like that, because it will make it easier to add more keywords in the future, and we're definitely going to add more keywords, like at least colon, right? So, and for colon, by the way, for colon we'll have to have true, so it's better to like have boolean per branch in here. Parse struct field is not implemented yet, so we actually fell through into here, so that means we kind of finished with that thing to some extent. There's some to-dos in here, of course, like pointed to, but I mean, nobody cares. Okay, that's cool. So what do we have? Struct define is not implemented. So we're trying to append a structure into the global structure array, and we can do that with append item as well, right? So this is going to be std, and let's just go ahead and do that. So size of struct, then the item itself. So this is going to be swap, and the array capacity is struct capacity. Though I should have called it structs, but I already made a typo, so it doesn't matter. So the array capacity, the array itself, structs, and then the counter, structs count. Right, append item, and if we didn't do that, that means we have a structs overflow, right? Structs overflow, and let's drop this entire thing. Cool. Compilation structs is not implemented yet. Okay, so we actually fell through, and all right, so I think parsing and compiling the definitions of structs is pretty much done. I would say. I think it's pretty much done. So we can remove this to do, and let's try to continue the compilation, and it should compile further. Report expected primitive type. Okay, so that's actually very cool. Right, so this is the change that we'll have to make now, right? So we need to parse not only, primitive types. We need to parse any sort of types. This one is interesting. Okay. So now we'll have to actually extend the way we represent the types, right? Because right now we only support primitive types and pointer types. So it's kind of interesting. The type right now is just two integers, right? It's just two integers. The first integer is the index of the primitive type, right? So it's a primitive index, as I call it. And you can find all of them in types in here. As you can see, we have 4 primitive types. Pointer, integer, boolean, and address, and this is basically like a value from 0 to 4, but we can easily add more primitive types, of course. And the second number is pointer counter. It's basically how many times a pointer to was applied to the primitive type. So essentially, if you have integer, for an integer, pointer counter is going to be 0, and primitive is going to be equal to 0, basically the index of the primitive type, right? So it's index of primitive type. If I do pointer to, it will increment pointer counter in here. If I do pointer to one more time, it will increment it even more. So basically, it's like how many pointer twos you have, how many levels of indirection for that specific primitive type you have. Right, so now we need to support pointers to structures. Right. The way I see that being implemented is that we have a fixed amount of primitive types, right? So we have values 0, 1, 2, 3. And we also know precisely how many primitive types we have. So essentially, if the primitive type is through 0 to 3, it is the primitive type. As soon as it goes 4, 5 and further, it is basically a structure, right? And it represents the index of the structure. So for instance, if it's 4, we subtract the amount of primitive types, right? So, and it's 4. So that means the index is 0, and that's the index of the structure definition in the global structure array. Right, so, and that way our like pair of numbers can represent primitive types, pointers to primitive types, and also pointers to structures and just structures, right? So with just two numbers, we can like move around quite a complex definition of a type, actually. So maybe in the future we're gonna actually have 3 numbers, right? Because maybe we're gonna have more than 2 kinds of types. Right, so right now we have only 2 kinds of types. The first kind is primitive types, primitive. The second kind is a structure. So maybe we're gonna have aliases, maybe we're gonna have unions or whatnot. I'm not sure if it's gonna be specifically unions, but you get the idea. So we're gonna have several kinds, right? And then we're gonna have 3 numbers. The first number represents the kind of type. Then the second number is going to represent the type like of that specific kind. It's going to be an index like of the primitive type, or an index of a structure, or an index of an alias, and so on and so forth. I'm actually not sure about the union, so I'm going to just like put a dot in here. Right, and then the third number is going to be pointer counter. Right, so we can make it even more complicated with just 3 numbers. And what's interesting is that right now, I think the numbers themselves, like pointer counter and primitive, are 16-bit numbers, because we're trying to pack them into 64-bit number. So it's easy to add additional information. It is needed for like for local variables and stuff like that, because we need to pack the type plus the offset on the stack into a single number for backward compatibility reasons, right? So it's kind of ugly, but I'm gonna fix that in the future. But yeah, so this is what we need to do. So I'm not going to introduce the third number right now because it's too much work. So I'm gonna just like use the idea of the primitive type being bigger than count data types or equal. That means it's an index within the structure array. I think I'm gonna go that route, and then we can refactor that. We can always make it better as soon as we have a better type system, of course. As soon as we have a better type system. So let's go. Maybe I'm gonna make a small break. I'm making a lot of small breaks, so because I'm a little bit nervous because of the situation around the world, so please forgive me that. But luckily it's all, fast forwarded for you anyway. All right, that took longer than I expected. So let's continue. Let me see what we need to do. So what was the error exactly? So an expected primitive data type, and we have this particular situation in here. Okay, cool. So let me try to do something about that. So it is not a data type, right? So we want to be able to look up structure. Do we already have struct lookup? I think yeah. But what's interesting is that we kind of need the index of the structure, right? So that means maybe we want to have something like struct lookup index, and here we're going to return an index and also indication that it worked. Let me put drop in here, and this one is going to be something like this. Struct lookup index, and I'm going to just try this. So we have a value, we have a name of this thing, so let me bind that to specific things, right? Data n and s. And if this thing is not a primitive type, we can do something like struct lookup index. And if this thing also not a struct, we'll have to say expected report expected data type, right? So maybe we can say expected primitive type or a structure, right? So like this is just a to do because I don't want to put like too much effort into coming up with like a proper diagnostic message. Okay, so after this entire thing is done, yeah, so this thing will return an integer that will have to drop in here, and this will return an integer that will also have to drop in here, but otherwise here we'll try to unpack the type. Interestingly, here I think what we'll need to do is probably add the amount of primitive types. So we'll have to do count data types and plus, right? Count data types and plus. And then in here, the only thing we do, we just increment pointer 2. So that should be enough, I think. So let me try to do that. And this thing is not implemented yet. Okay, fair enough. So here we have a name, right, and let's create an index. And while the index is less than the struct's count, right, while it's less than that, we're going to keep doing this thing. So let index, index 1 plus. I can take the index, multiply it by the size of the structure, and offset with that, right? Offset with that, and that gives me the specific structure in here. I might as well actually do it like this, so this is going to duplicate, and now I have a struct, right? And in here I can do struct name pointer plus, read that name, and just compare it with this thing. Might as well put something like this in here, str equal, right, and if it's equal, that means I can just return the index like so. Okay, otherwise I continue doing this thing. Cool. Interestingly, no, I think it's fine. Do we need anything else? I don't think so. And here I can just like, actually I need to return true in here, true and index. And then here I can just return false. Yeah. So what I'm thinking is that here I can duplicate this thing, then I can go further and just do something like that, and then do an str equal, and if it is true, alright, the only thing I'll have to do, I'll have to just do true return, and otherwise it's going to be 1 plus. I think this is shorter, right, especially if I do something like this. So here I turn an index into a pointer to a structure, then here, actually I have to do something like this, I get the field name, right, and then I compare that field with the expected name, and if it's true, I just return true and continue the stuff. Okay, once we get like proper structures, I think this code is going to be a little bit more readable, hopefully, right? So also maybe we're going to have some special syntax for arrays as well, right? So it's a little bit easier to access elements of the array. So all of that is going to be way more readable after I'm done with structures and arrays. I do have plans for arrays as well. Anyway, so let's try to compile the entire thing, and unknown word. Okay, so the compilation went quite far away, as you can see, right? So that's pretty cool. So I don't even know what we're gonna do in here. So let me, for now, by the way, we're only gonna have something like this, right? So we're not gonna have any specific names, only this kind of stuff. And it didn't even complain too much. So I think for now, I'm gonna just like try to push the variable onto the stack, right? So, and here, as you can see, it fails with unreachable because it doesn't really know how to print the types with structures, right? So let's go to the types, and this is 100, and there we go. So this is basically where we fail with unreachable. So in here, we'll have to do the following thing. So let's take the primitive thingy and check if it's within the boundaries of this structure array, right? So probably have to do something like count data, and we're gonna subtract it, so that will turn it into an index, and then we can check is it less than the 0. If it's less than the 0, that means the struct index is too small, right? Struct index is too small. Otherwise, structs count greater or equal. We can do struct index is too big, right? And after that, what we can do, we can turn this index into a specific, into the pointer to the structure, right? So size of struct multiplied, then structs plus pointer, right? So that gives us that. And then I can take the struct name, pointer plus, and then read it as a string, and then TMP append and drop. Right, there we go. So that's cool. All right. Unknown structs count. Oh, this is because, yeah, I do remember that. So I just need to move the structs to the type module, so to speak. We don't really have a module, but it kind of acts like a module. It's a separate file. Right, so let me put it somewhere here. I think I'm gonna have maybe like a begin struct, and then something like this, and struct. Right. So, and let me see. So it's still not gonna work. I think it's still not gonna work, right? Because I think we need to move display type a little bit down. We need to move it a little bit down, like so. So, and then we have type stack, so which also can be moved a bit down. All right, so now we're talking. We have unhandled data on the stack, which is a pointer to string. Okay, that's cool. So let me do a committee. So what did we introduce in here? We introduced structures, literally. So that's basically what we have in here. Introduce structures. Right, so we're introducing structures. So now we need to probably do something interesting. Just a second, I've got a message. So as far as I know, right now, when you define a variable, the size of the allocated variable is pretty much hard-coded to the size of the word, which is 8 bits for x86, x64. So now the sizes of the structures are bigger than a word. So this has to be reflected somehow. So let me actually do that. And OP, is it going to be OP? Maybe. I'm not quite sure. I think we need to look for keyword var. Right, there we go. So keyword var, and in here, as you can see, yeah, so we basically always allocate 8. So what I'm thinking is that we need to introduce a way to get the size of the type, right? So let's introduce size of type, and we're gonna get the integer, which represents the type, and then it will return the size. Okay, so here we have type. We might as well unpack the type, turning it into the pointer count and the primitive, right? But the primitive itself can be, again, like also structure, right? So we have different situations in here. So the first one, if the pointer count is greater than 0, right? It is greater than 0, we can instantly say that this thing is 8. Right, we can actually use early return, right, something like this. So if it is equal to 0, less or equal than 0, but primitive type is less than the count data types. I should rename the data types into primitive types, right, because it does not really reflect that it's data types, right? The type system is more complicated now. If it's less than that, the size is that. Right, if it's equal than that, we have to take primitive and essentially subtract this thing. And we also need to check whether it's not bigger than the amount of structures. So I'm going to take the code that I wrote in there and extract it into a separate procedure that takes the type and turns it into a structure, right? So that's what we're gonna do. Prop struct of type, which is kind of a weird thing, right? But I guess that's fine. So this is the integer and this is the pointer, right? And this is what we're gonna do in here. We can just take the entire thing, copy paste it in here. Right, so this is like that, then we duplicate, right, then we take this thing and we just return whatever we've got. Yeah, cool. Struct of type, and that's what I can do in here, I think. Up until this point, struct of type, like so. And then we get the name, and we read the name, and we append it in here. So that should work. I wanted the compilation. Okay. And in here, what I need is struct of type. So that gives me the structure. And then within the structure, I just need to iterate through all of the fields that we have in there, right? So this is a struct, like so. But what I need in here is the field and the amount of fields. Right, so what I can do is just duplicate struct fields, pointer plus, and read it as a pointer, and then swap. Then duplicate struct fields count, pointer plus, read it as an integer, swap. So that should give me the fields count and the struct. Right, but I don't really need the struct after all of that, so I can kind of like drop it, right? So yeah. So I only need fields and count. And I can now even organize a loop, right? So while dupe is greater than 0, we're going to do the following thing, right? So here we have the field and the count. And at the end of all of this, we're going to do field size of field pointer plus and count -1. So, and then here we can just access the field. And within the field, we can take the field type, right? So it's going to be pointer plus field type. And interestingly enough, we need to accumulate the size somewhere, right? The question is where we're going to accumulate this size. So here is the structure, right? So I might as well put the size somewhere here, right? So this is going to be 0 and this is going to be the size. And we're going to just do it like that. So the size field and count. Then I take the type and I read the type as an integer, take size of type, and then I add that to the final size. And thus we continue the loop, right? At the end of all of this, we're going to have the size and the field and count that we don't care about, right? And we can just return the size like so. Cool. Yeah. So that's the original size, right? Which will be bound in here, hopefully. So, and in here, we just like prepare for the structure, then we extract some of the fields from the structure, and so on and so forth. Hopefully that will work out, but the compiler will tell us if something is wrong. Let me see if something is wrong. Everything seems to be okay, so everything seems to be compiling. And now I should be able to just use that in here, right? So I can take the variable type, so it's a variable var type pointer plus, right? So we've got that. Then I can read that as an integer and say size of type, and that's going to be the size by which I increment the, allocate the variable. So similarly, we're going to replace this thing in here, right? Like so. So yeah, and that means that we should be allocating this stuff in here. Okay, struct index is too small. Why is it too small? I'm not quite sure. So I think I already encountered that problem before. I'm just not sure where I'm getting that. Struct of type. So there's one place when we're trying to print the entire thing, and I don't think we're trying to print it, and there's another place when we are... Oh, because the minus is done by the struct of type, so we don't really need this kind of stuff in here, so that's fine. Okay, so everything seems to be compiling, so let's actually do this thing. And what do we have in here? All right, so I suppose the variables are of the right size, hopefully. We can also check that, I think. Let me go to the... Oh boy, to the main, maybe not main, but it's a different main, right? So this is going to be something like this. Dump ops, right? So this is a dump ops, and I can iterate through all of the variables, I suppose. So this is going to be global vars, right? So only care about global vars, and global vars count, right? And while dupe greater than 0, in here we do let gvar and the count. So gvar var location pointer plus e put lock. Alright, so then this thing e puts gvar var name pointer plus string string e puts. Alright, then another thing e puts, and in here we'll have to do gvar var type pointer plus integer type of size of type, right? Size of type. E put u, new line e puts, right? And in here we can do gvar size of var pointer plus count minus 8. 3 align input, and there we go. So in here we'll also do drop. Cool. So the thing I want to do actually now is just make it compilable, right? Just make it compilable, and use dump. This is not what I wanted, but okay. Alright, so this is what we've got, and we've got some variables in here. So this is a random state, All of them are 8 bytes, but this one is 16, which is the size of the entire string, which is absolutely beautiful. Love it so much. Okay, that is very, very cool. That is very, very cool. So the next thing we need to do, we need to implement the ability to offset by index of the field, right? So we want to be able to do the following thing, like name 0, right? And that should turn it into a pointer to an integer, pointer to, like this. So yeah, but before we do that, let me actually commit whatever we have, okay, maybe I don't want to commit that because it was just like a temporary debug thing. So this is the compilation. All right. Allocate variables based on the size of the type, right? So, and I'm gonna push that right into the repo just in case. So let's go ahead and introduce the second keyword of the day, which is the colon, and see how it goes. I think it is going to be interesting. So now I'm gonna go to the Lex Porth. Let's find the keywords. So how are we gonna call this thing? Keyword. Let's call it keyword field, right? So, and the keyword field is going to be basically the colon, right? So let's go ahead and do that. What do we have in here? 25. It's going to be 26, right? 26, and this is that. Though Porth actually allows us to call it keyword this. And it will actually work, believe it or not, because like you can just use a colon as part of the name. Because why not? But I'm gonna call it field. It's a little bit more readable, I think. Okay, so 25, 26, right? 26, and this is field. All right, and this is gonna be that. 25, 26. What do we have in here? This is the compile time evaluation. I think the field, the support for fields should be in a compile time evaluation, because you may have a constant that constantly points at a field of a particular variable, because why not? Right. So the position of the variable in the memory is constant by definition. So why not just like not allow to do something like count and just do name 0. Right, and that just turns it into a pointer to that specific field, which you can just push in here, right? You can just push in here and then do your thing. For example, read it, right? So yeah, because a pointer is just a number, right? So you just store a number in the constant. I think it's an interesting idea, but I don't think I'm going to be implementing it right now, right? So I'm probably going to implement that specific thing off screen. I'm going to just put some sort of like a to-do, right? So else dupe keyword field, and I'm going to do something like to-do const eval field keyword is not implemented in const eval yet. Right. Though const eval is going to be reworked in the future, right? So my idea is that when the type system is powerful enough, I'm going to sort of factor out the context of the compilation, so to speak. So right now, the whole context of the compilation is just a bunch of global arrays. I want to consolidate them into a single structure, which you can duplicate. Right, so you're going to have like several compilation contexts. And for instance, for compile time evaluation, I want to have a separate compilation context. So yeah, essentially evaluating inside of a const is going to support pretty much the entire language. I don't know what kind of limitations we're going to have, we'll see. Pretty much the entire language. And it's going to be compiled in a separate context, evaluated in a separate context, and the results of the evaluation are going to be embedded into the actual program, right? So we're gonna have like a full meta programming in the future, not right now, of course, not right now, but in the future. So that's why the compile time evaluation right now is super hacky, because I don't care about it. It's gonna be like wiped out anyway. Right, we just need something that sort of resembles compile time evaluation for some specific cases, just to get by until we, have a proper type system, which makes it easy to create a structure, the context of the compilation. Okay, so this is what we have, 26. Let me find keyword struct. So this is a keyword struct, and then here we're gonna add another keyword. So keyword field. So it's gonna be to do compilation of keyword field of the field keyword probably is not implemented yet. There we go. Okay, unsupported word name in compile time evaluation. Makes sense. Though, interestingly, yeah, okay. Ooh, that's cool. So we do not look up variables, but that's going to be also a separate thing that I'm going to implement later. Might as well also just put it to do for that. Right, because as you can see, we probably look up things in there. Yeah, I kind of want to put it to do. Just a second. So unsupported. Maybe. Unsupported word. So here we look up different things. We do constant lookup. Do we do any memory lookups? I didn't think so. I didn't think even memories work right now. So if I allocate, if I make this a memory, right? If I make this a memory, I think it's still not going to work. Right. Yeah, so we don't even support memories, so I should not worry about that. So nothing is supported in compile time evaluation because it's going to be dealt with a little bit later. So let me just remove that and continue implementing these things. So compilation of the field keyword is not implemented, right? And we can also do something like locate it here. Okay, so and then if I take a look at that, as you can see, it is located in here. Cool. So what I want to do now is to take the word after that keyword, right? That's what I want to do. It kind of resembles the parse name of the definition, right? But this time we're not taking the name of the definition, we're taking the name of the field. So it does precisely what we want, but it generates incorrect diagnostic messages. So right, so maybe we could basically factor out the error management for this function outside of the function itself. Right, so as you can see, it returns a string. We can return a boolean indicating whether it was successfully parsed or not successfully parsed. But at the same time, you have two types of errors, right? The end of the stream of the tokens and not correct token. So I'm not sure. So that means this boolean has to have three values, right? So success or a failure, and a failure is going to indicate the what exactly is the failure, right? So what exactly is the failure? Which is rather interesting, right? So I don't know. And that means I have to introduce like a enumeration, right, for different types of errors, like for OK, then for end of file, and for incorrect type or something like that. Which is kind of annoying, and I don't really want to do that. So I have an idea. We can say expected word but found nothing. Here we can say expected a word but found this thing instead. So we can basically, if the trend in this language development was If a particular diagnostic doesn't fit what you need in a particular procedure, you just make it more abstract, right? And now it fits, right? So now it doesn't even mention the name or not name. We just say expected word but found nothing. And we can now call this thing parse word, maybe parse next word. Easy. I mean, just make it more abstract. Right, and now you can reuse it for anything. So yeah. So parse next word. Cool. Compilation and located here. So in here I can do Lexa parse next word, and that should give me a name, right? So this is going to be a name. Ooh, and this one is rather... Oh, actually, we're not parsing fields by name. I completely forgot about that. We're parsing them by index. So that means we need a similar function, but the one that actually expects integers. I have an idea. What if we call it parse next token, and in here, along with the token, we're gonna expect the token type. We can say something like expect token, right? And in here we're gonna accept the Lexa and the token type, right? So this is a token type, and that thing, though right now it returns some sort of a number, we should probably return the token itself, right? But if we're returning like a structure, we probably need to allocate it somewhere, so we can try to allocate it on the temporary buffer. So this will be the size of token, tmp alloc, let token in, and there we go. So we're gonna put it in here, and here we're gonna actually return the token. So this is something like this, and there we go. So here's the token, here's the parts of the token, though we can move the Lexa in here, right? And also token type, right? Let's call it expected type. Right, so here we have expected type, then the Lexa, then the token that we allocated, then we just basically spill the token in here for different fields. And here we can say that expected this, right? So expected inputs, and we can say something like expected type, human singular, token type input, I think. I'm gonna line input. There we go. So the expected but found nothing. Expected. So we'll have to repeat that as well. Expected. Something like this. No. Just put it like that. All right. So it's going well, I'd say. Align input. Cool. Oh boy, expected type, Lexa token, then we destructurize that, and then we just check all of these things. Yeah, I think it's a good idea, actually. And it's going to be reusable also for asserts, right? Because assert is kind of similar, right? Assert expects a string. So yeah, that should work. I like that. I think it's a good idea. Okay. So also I think this has to be like a space. Oh right, a known word parse next word. So expect token. So provide Lexa, and here we have a token word, right? Specifically we expect the token. Though just a second. Expect token, right? So this is expect token. We just return the token, that's quite important. And here, right, we have to actually treat it as a token. So that means we have to do token value. This one is rather unfortunate, right? Because we're returning the pointer, don't we? Yeah, we do. Token value pointer plus, and read it as a string. So this is what we've got, right? Expect the token, extract the value, And there we go. So as far as I know, somewhere down there, we also rewind we do TMP rewind on each iteration, so that means we can quite easily just allocate stuff in a temporary buffer, and that's fine. So expect token one more time. So this is a token word, and everything's fine. Cool. Here, expect token. We expect also token integer. Oh, this one is interesting. So since in the future the field is going to support integers and words, expect token need to be modified to actually accept several token types, right? So we can say you expect integers or you expect words. Something like that. We'll see. Anyway. So here specifically we expect an integer, so I can do token value pointer plus and read it as an integer. And here we have index or field index. Right, field index. And now we also need to know. Oh, we don't have this specific structure in here. Believe it or not, we don't have a specific structure because we, at the compilation stage, we only can know the type of a specific structure at the type checking phase. So that means we have to create a new instruction for the intermediate representation. So let me quickly do that. I think it's going to be something like OP struct maybe field of set, right? So it's a field of set. Push OP, right? So field of set, and then we're gonna just use field index, and then we're gonna use the token, right? I think. So what token are we gonna use? Push OP. I guess it's fine. Yeah. Push OP. All right. OP field of set. We don't have such thing. Let's find all of these things. Const OP field of set. One offset. To do document OP field of set. Instruction. There we go. So we'll have to go through all of these things. 28, 29. Right. So then we're gonna do field offset. Field offset, and then here 28, 29. What is that? Is that what? Ooh. Oh, I think it's a. I think I know what it is, because sometimes, yeah, I don't think it's neat. So, what's the other thing? Type checking. Yes, type checking. Please give me the type checking. Local var. So let's do something like else type int op field offset, and we can say something like type checking field offset is not implemented yet. All right. Okay, and during the generation, ooh, this one is also interesting. OP push global var. So this is a local var, and OP field offset equal this do generating code generation for OP field offset is not implemented yet. Okay, so what we got? Expected an integer but found an integer instead. I know exactly why that happened. It's just like funny. Okay, so let's go to the expect token, right? So the reason why it happened is because we need to compare that with expected type, right? So let's continue. Okay, the compilation is not implemented, compilation of the field keyword, but it is, so I can remove that thing from here. Yeah. So I just expect an integer, then I just extract it, and that generates a new instruction, OP field of set, which can be resolved at type checking, I suppose. Though we kind of lose information during the generation. Oh shit, this is kind of interesting. So we have several steps, right? So we have a compilation step, compilation, then type checking, then generation. We don't know the type of the structure, the type at the top of the data stack at compilation step. We do know it at type checking step, and we forget it at the generation step. Right, so the intermediate representation instruction set is shitty, but that's okay because I'm trying to basically pile features on top to see where the features create friction with the current instruction set for intermediate representation, so I have more information on how to refactor it and how to rework it. So that's totally fine. So all of the frictions that I have between what I want to implement and what the intermediate representation can do is a good thing because it's a gathering information, so that's fine. So in compilation, we don't know the structure. At type checking, we do know it. At generation, we forget it, but we do need it. So here's an idea. We can do the following thing. The type checking will interpret the operand of OP field of set as an index of the field, and then it will figure out the offset and change the meaning of the operand to be an offset in bytes. And so during the generation, we don't need to know the type of the structure. We can just like use it as an offset, which is rather interesting. So that means this makes the type checking stack mandatory for the language to work properly. So remember how like I introduced like unsafe flag and stuff like that? I actually removed it, then I brought it back because it was useful for some situation because the type checking was slow. Right. So that kind of forces us to remove this flag because structs literally cannot work without type checking. Right, so they can't function. Type checking becomes the essential part of the language, and there is no two flavors of Porth anymore, like safe, like type checked and untype checked. There's only type checked one. Everything that is not type checked is not Porth anymore. So, which is really freaking interesting. It is insanely interesting. So basically type checking will change the meaning of the operand, or maybe we can transform that into a different operand. But I don't think so, because we can just transform it into like adding a particular number, but that's two instructions. So yeah, I don't know. Interesting. Yeah. So, and I kind of predicted that when I started this entire thing. So I thought that at some point we're going to depend on type checking so much that it's going to become essential part of the language, and we like won't be able to keep this flag anymore. So yeah, that's fine. Rather interesting, rather interesting. Okay, so compilation of the fields is not implemented. Type checking field of set is not implemented. We are about to do the type checking. We are about to do the type checking, so... Is that even a good thing? Oh yeah, I know what it is. Yeah, it's for local variables. I shouldn't worry about that. So how are we gonna do that? We need to expect a single element on top of the stack. And the type of that element has to be a pointer, right? So basically the pointer counter has to be at least 1. And the actual type within that pointer has to be a structure. And if it is not, we'll have to throw an error. So let's introduce something like type check field of set, right? So in here we'll have to provide the token and the stack. Right, and then we just go to the next operation. Right, and essentially in here, right, so we'll have to expect a particular thing. We will check that it's the type has you know, appropriate shape, and then we're going to construct inputs and outputs and just feed all of that into the standard type checking system. So should be fine. Though it will also This could be complicated because the type checking can visit as the same instruction 2 times. It can visit the same instruction 2 times, and when you visit the field of set 1 time, we're going to change its meaning from index to offset to in bytes. Right, we're going to change its meaning. And when it's visited the second time, we have to catch that moment and not type check it anymore. So this is rather interesting. So that creates a little bit of friction in the type checking system, the current type checking system as well. Though we can try to store the offset maybe in a half part of the word or something like that. Interesting. So yeah, I'm gonna make a small break, and after the break I'll try to come up with something. Alright, this is a tough one, and I think we'll have to transform the instruction during the type checking. Right, I actually want to rename this instruction to something else, specifically saying that it's a field index, right? So this is a field index, and it stores the index, and after type checking it's going to be transformed into field offset, which is going to be in bytes. But on top of that, I also probably... I'm not quite sure, because again, during the type checking we can visit the same instruction several times, and the instruction has to be performed, could be performed like type checked several times. And if we replace index with offset, we won't be able to sort of retype check it later. So that means that offset also should store the index. So it is possible to retype check the instruction afterwards. It is important because as the control flow merges, we evaluate the instruction the second time and confirm that the state of the stacks is the same, though the specifics of the type checking could be changed, and maybe at some point these two instructions will be merged together somehow. But again, we have a lot of friction when it comes to like trying to fit what I want into the intermediate representation, and that is good. We're gathering information of what it's needed, right? So far we understood that you know, the type checking step transforms the intermediate representation, and maybe we should have several intermediate representation, right? The first one after the compilation, after the first sort of translation, sort of like the rough one, like more high level one, then we can resolve all of the overloaded stuff, like you know, accessing the fields and stuff like that, and then maybe we're gonna like have even lower level intermediate representation. So far we can see that, which is good. We're gathering information, so that's fine. But right now we need to implement a working feature. As soon as we have a working feature, we can start using that feature in the language itself, right? So that's a very important thing. Even if it's not perfect, it's still usable and can be used to further improve the compiler later. Okay, so I'm going to introduce the index, right? So I just need to do the renaming super quick. So this one is going to be index. Right, and what do we have in here? This one is the index. Cool, and this one is an index as well. All right, so in here we have type check field offset. Okay, so I need to go to proc and just see type check. So here we accept the pointer, which is the token, the current token. We type check and add the stack. And in here, we're just gonna drop both of these things and say that this thing is not implemented yet. Type check field offset is not implemented yet. Right, it is not implemented yet. So let's see what we have. So this one has to be an index. So where are we? It's a code generation. So this is an index. Interestingly enough, so index should never reach the code generation, only OP field offset. So here we can say that something like unexpected instruction in code generation type checking should have removed it, or should have replaced it with OP field offset. Right, so that's basically what should have happened. So it's an insertion. It should never happen. Okay, so the next thing, type checking is not implemented yet, and this is precisely what we have in here. Cool. So then let's introduce the second one as well. Right, OP field index, and this one is going to be OP field offset. There we go. So this one is going to be 30. Right, this one is 30, and this one is offset. Right, cool. So what we have in here is, I don't think anything needs to be done in here, so that's fine. The next one is in the type checking. Okay, OP field index. Okay. Else type int OP field offset. Right, and in here we do the following thing. Type checking OP field offset is not implemented yet. Okay, cool. Next one, generation, OP field index, and offset is the one that needs to actually happen, right? OP field offset. Right, to do. Code generation for OP field offset is not implemented yet. All right. Okay, so now, of course I forgot to increment the thingy-majingy. Right, and yeah, so we are about to type check this entire thing. Cool. So I suppose I need to do expect arity. Expect arity. So here we provide the token, the stack, and the amount of arguments we expect on the stack. So I can do over, and 1. I expect only 1 argument. Expect arity. So that should give me the stack, right? That should give me the stack. On top of that, maybe I'm going to allocate the output stack too. So type stack tmp alloc, and here we have ins and outs. So might as well actually do something like this. We're going to remove that later. So the ins will have 1 argument, and that argument has to be pointer to a structure, right? If it's not, well, that's bad. That is bad. Check field offset. Okay, so let's just go ahead and do that. So ins type stack top pointer plus, and I'm going to just read it as a pointer. So that gives me a type frame, and then I can do type frame type pointer plus and read the type. Right, so that gives me the type, and then I can unpack the type, right? So I unpack in the type, and then here I have pointer count and the type itself, right? So the first thing, if the pointer count is not equal to 1, interestingly enough, I think it is always has to be equal to 1. Right, because we should not support things like pointer to string, right? So we won't be able to do offsets on that one, right? So I think pointer count always has to be 1. If it's 0 or if it's greater than 1, it's not going to work. right? At least for now. Maybe later it will. So has to be equal to 1. If it's not equal to 1, right, we're gonna do something like that. So what we're gonna say? Ooh, here we can do token stack. Right, so let's do token stack. So token location pointer plus put lock, and in here we're gonna say an error. So what we're gonna say, we need to say that unexpected type, right? So expected pointer to a structure, right? So that's what we can say in here. Puts, and then it's going to be exit. And we can do the same thing for a type. Type has to be greater or equal than this thing. If it's less, we can kind of do the same thing, can't we? I can even probably merge these two things together, right? So if it's not equal to 1, or it's a primitive type, that means, well, it's not a good fit, right? It is not a good fit. Okay, so now we have a structure, and the thing we need to do, we need to struct. I forgot how was it called, type. So the one that extracts the type from the structure, or structure from the type. I really forgot how it's called, to be fair. Struct of type, yeah, that's what I wanted, right? Struct of type. Cool. So, and struct of type gives us the pointer to the structure definition, which we can use, right? Which we can essentially use. Oof. Right, and we need to have the pointer, we need to have the index, right? So we need to pass the index, that's very important. So maybe we're gonna accept the index in here. Int field index, right, and field index in here, right. So this is the structure, and I'm gonna do it like that. So let me also find this thing. So we'll need to take the operand. Is operand, okay, operand is a pointer. Right, the operand contains the index, and we feed that index into the type check field of set. And we're using that index in here. So now we have a struct, right? So we have a struct, and we can check different things. So struct fields count, pointer plus, we can read it as an integer, and if the field index, right, the field index is greater or equal than this thing, we're gonna say that it is an incorrect field index, right? Also, it could be less than 0. So field index 0 less, or that. Token location pointer plus put lock error incorrect field index. Okay, cool. So incorrect field index, and then we can do the thing like so. So we take the fields, right? So here is the fields, and we know that the fields is the pointer, is it? Right. So const size of struct. I'm not sure where is it defined. Oh, it's probably defined in the type. Yeah, size of struct. So it is a pointer, so we have to read it as a pointer. Then we can use field index size of field multiplied, and we can offset that pointer, and we get the pointer to that specific field. Right now we have a field in here, which we can use. That's very cool. So, and within the field, we have the type, right? And by knowing the type, actually, because we don't really need the type, we need the offset, right? We need the offset, and that means we have to just take the index, iterate through all of the fields before, and just, yeah. We can do the following thing. I can just introduce field offset pointer plus, right? So this is this thing, and we can even do something like this. And then we just read it as an integer, and we've got the offset. And what do we do with that offset? We have to give it to, I suppose, whoever called this procedure, so we can just return that offset in here. Yeah, the offset. So, and then whoever calls this procedure can, like, reassign this entire thing. I suppose. I think. So let's see if it works or not. I don't know. So unknown word field offset, precisely what I needed. Field const. So field offset, and we're going to assign that offset as we parse the fields, right? So you have field push type, which is rather interesting, actually. What if we also maintain the size of the structure? As you push more... Well, no, it's not going to really work that well, unfortunately. Okay, so I suppose we'll have to parse... So I suppose it's a compilation. Parse Fields. Man, I already forgot. Keyword struct. Okay, there we go. And what do we have? Parse struct fields. Where is it? Okay, so here it is. So we have some fields and whatnot. And we push the field in here. Right. That is very cool. So field push type, and I think this is where we have to also accept the offset that we're setting in here. So we only accept the type. So this is the type, and we're also going to have offset. So this is the field, and then field offset pointer plus, and we're going to save it in here. And there we go. Cool. There we go. Now, let's try to recompile that. So that should break in field push type. That's expected essentially, but what offset do we put in there? That's a very good question. So where do we keep track of the offset? We can keep track of the offset in here. So this is basically going to be the size, right? So this is the size, and we keep track of it in here. So, and in here we have the size. So this is true. Size and the type, right? So size and the type. And we push all of them in here. So this is going to be size type. And then we are going to add size of type. Actually type has to be in here. To that thing. Interestingly enough, I think we can easily just do over, and then size of type, but it makes it completely unreadable, so I'm going to keep it in here like that. So yeah. So yeah, I push the size as the offset and then I increment it. So this is basically the automation of, you know, generating offsets for all of these things. Right. Okay, cool. So pointer div. So, and once we got that thing, so this is actually very cool, isn't it? I think it is. Because we can use that size to store in a structure itself, and every time we need to get the size of the structure, we can just get it from the structure itself. Right, but I don't think I'm gonna be doing it right now, so I'm gonna just like put it to do in here. Cache the size of the structure. Right, so this is what I want to do in here, but for now I'm gonna just like drop that. Put it in here, and there we go. Okay, so unexpected data on the stack, and what do we have in here? Why do we have unexpected data on the stack? Probably because we returned something from type check field of set, right? So, and for now, we'll have to essentially take that offset and reassign it to the current thing. So yeah, what we'll have to do is set the field, the type, to OP field of set. So as you can see, type was index. Now we're setting it to be field of set. Then we take the offset and we set that back to the operand, right? So the operand, like so. Because this entire thing just returns the offset. But I don't think it's going to be enough, right? Because again, as I already mentioned, I want to preserve the index. So my idea is that I'm going to store the offset in the lower 32 bits of the word and the index in the upper 32 bits. And then I'm going to reuse the same thing in the field offset. It looks weird, I know, but this is because, again, there's all the frictions between what I want to do and the model that I built for the language, which is good. That means I know how I need to change the model, right? So all of the points of friction can be then fixed later. Okay, so I keep, you know, coping with that idea. Right. I'm gonna fix it. I'm gonna fix it eventually. All right. So let me think. So we've got an offset, so we can just use it like that. Also, I'm gonna take the operand. Right. So this is the original index. Might as well just assign it like this because I'm gonna be using it quite a lot. Right. So this is the index. And then I take the index and I just like, you know, clean it up with the end, right? I clean it up with end and then I move it, shift it to the left, right? So I shift it to the left, so that means this entire thing is prepared. Then I essentially take this offset and also clean it up, so I can even like align them together so it's clear what exactly I'm doing here. Right, and then I OR them together, I pack them together, and I save them back into the operand. Right, so, and of course the type of this thing now becomes a different type. All right, so that's what we have, and we just continue doing the thing that we're doing. So, and the next time we visit this operation, we're going to be type checking OP field of set, and we can type check it just like OP field index and then compare their offsets to make sure that everything okay. Right, so that shouldn't break the type checking. Again, the type checking is going to be changed accordingly to the friction. All right, so struct index is too big. All right, that is very interesting. Struct index is too big. Struct of type. So this is a primitive. I wonder where that exactly happened. So let me find struct of type. So we're using it in here. So we're probably using it in here, right? So type is less, so we exit. It has to be greater. So I might as well just do something like this. And eputs, then type and print, and I suppose right before this thing. Ooh, this is interesting. So that happened not here. That happened not here. So let's actually keep checking the other stuff, right? So what do we have in here? Type check field of set. So that's happened really not here. Eputs. So let's find other struct of type. So struct of type. So this is the second one. I don't think it happened here. So this is a display type, right? Display type. Unknown word type, so because it's a primitive. Okay, that's very interesting. Struct of type. So it's happened here for whatever reason. Size of type. Alright, so let's see. Why did that happen? Size of type. Ooh. Struct index is too big. Size of type. And then how many places we use size of type? So it's for calculating this thing, and then it's probably happened in here. Size of type. Field offset const. Ooh. I think it has to be an integer, but I'm not sure if that's what caused this entire thing. I don't think so. Right, it has to be an integer. But yeah, I think that's the problem in here. I mean, we can try. Size of type. It almost feels like, did I assign index to the offset or something like that? I think that's what happened. Just a second. Field type. And when I assign, oh, I think I know what's going on. Okay, field type, and let me find this thing. It has to be the other way around. Okay. It has to be the other way around. And that thing, yeah, type check offset is not implemented. This is precisely what I would expect. So this thing is basically implemented. So let me find all of these places. Ooh, yikes. Why do I have so many of them though? Struct of types. So let's actually go through all of these things. Struct of types. I'm gonna remove that. Struct of type. So that as well. Struct of type. That as well. Cool. Let me see. Okay, so this is not implemented, but it is implemented now. Right, it is implemented now, so everything should be okay. And the rest of the thing. Okay, so now we... That's very cool. But it didn't work exactly as I expected. And handle data on this... Well, yeah, that really didn't work out correctly. I wonder why. Because I didn't actually perform the type check, and I think I know. Right. So, type check field of set. Type check field of set. So, and in here, what I have to do now, once I prepared everything, right, so I checked the input type, and now I need to create the output type. And the output type is going to be the type, the pointer to the type of the field. All right, so I have to do, so I need the field actually. So yeah. So here is the field. Field and I need to prepare the out, right? So let me see. Type stack push. Stack push. we usually provide the type, and the type we're gonna have is field type pointer plus, but it has to be a pointer, so it's gonna be something like pack type, right? So we're also gonna read that. So we take the type of this thing, pack the type, then outs, and then we do type stack push, right? Just type stack push, and there we go. We have outs. Type check stack, right? So we provide the token stack and ins and out. Token stack ins outs type check stack, and there we go. After that, we just return the offset of the field, which can be used for all of that. There we go. I think we can try to do something like this, right? Should be fine. Should be fine. Okay, argument push pointer, but got an integer. Oof. Where integer was provided in here. Pack the type, type check push. But I mean, it has to be an integer. Expected type was declared here. Oh, I have to provide the location. So the location is the second one, so we can take that from the token. Did I? No, I didn't. So that means I have to directly do token location pointer plus. So we got that, and that, and are we ready? And oh my god! Yes, we have a name. So we have a pointer to a string, and then I do that. Ooh, that is juicy. Huh. And if I do something like 1, right? That is pointer to pointer, right? And if I try to, for instance, maybe read this entire thing, and handle data, we can try to print this entire thing now, print the size of this entire thing. All right, so, and that didn't really work out correctly. I would like to generate some code because, yeah, code generation for the field offset, that's what I would like to have. Code generation of our nation. Okay, so essentially what we have to do, we have to take the pointer on top of this stack and add the offset to that pointer, and that's basically it. So it actually depends if the offset is 0 or not, right? So we kind of already have that stuff, right? Anyway, so I can do operand, and it's already read for us, so should be fine. If the operand is greater than 0, only then we're gonna... Oh my god, what the hell has happened? Emacs. Okay, so if the operand is greater than 0, we'll have to do something. If it's equal to 0, we don't have to do anything at all. And the thing we're gonna do is essentially add... can I just like add a value like this? So it's gonna be bfd bputs, and then operand bfd bputu, and then a new line which is bfd bputs, right? bfd bputs. Cool. So yeah, we're just like adding the offset to the pointer that is on top of the stack, and I hope that will work. We'll see. I mean, the compiler, the assembler is going to complain if it's not possible to do that. And it is apparently possible to do that, which is kind of cool, I think. I think it is kind of cool. Right, so what if I try to run this into, I think it will say 0. Interestingly, can I now save some data into here, right? So can I just like assign, you know, 69 to that specific thing, right? So can we assign that? We did assign it, and then can I read it back essentially? Right, so it should now say 69, and holy shit, it does say 69. So That's pretty cool. So I can access specific fields like that, and it is working. So of course the feature is not particularly finished. I created a lot of different to-dos, a lot of assertions and stuff like that, so I'll just have to go through all of the cases. But the basics of the structure actually works, and that's cool. So what if I take the name and try to just read it and like print it? Is it gonna work? I'm not sure. Or like it did in fact work, but it's should not actually. It should actually not work. So something is hard-coded somewhere to just read 8 characters, right? So that's what's going on. So I think we need to forbid doing like at on a non-primitive types. Right, we need to forbid doing that. Also, we cannot use structures within the structures because it's not, you know, explicitly coded. So if we have something like this, right, it's not going to work, I think. So if I try to compile that, it will say str is not a type because we don't look up structures to be within the structures, but this is something that we'll have to implement. Okay, so let me actually go to, you know, intrinsic load ptr2, right? And during the type checking, so we do type check load ptr2, and here specifically we can only accept ptr2 types, and then we just dereference it. Okay, so that's kind of something that we should check in here. So prim has to be less than the count data types, right? So it has to be less than that. So this is going to be lock, put lock. So the reason I'm not allowing to dereference structures is because they may not fit into a single word. Right now we can only have words on the stack, and the structure doesn't fit there yet. So I'll think how we can solve that, right? Maybe we're going to allow just reading the structure into you know, dereference it and putting it on the data stack. So, and if the structure is always aligned by the size of the word, it should be relatively easy to take the structure, chop it into words, and just put all of these words into the data stack, but on the level of the type system, treat it as a single item. So it shouldn't be that difficult. So maybe in the future we'll allow to store structures by value on the stack, but not for now because it will require like additional work or something. So right now I'm gonna just you know, disallow that, and it doesn't work anyway, so whatever. Cannot dereference structures, right? So if I try to do thing like that, it will say str is not a type. Well, I mean, let's actually remove this thing. Okay, cannot dereference structures, and it points. Ooh, this is bad. If it's greater or equal. The other way around. Yeah, there we go. So you cannot dereference that, but if you reference to a specific field, you can dereference that. The same goes for this kind of thing, right? So the same goes for this kind of thing, but I don't think it's gonna work that well anyway. Oh, it just allows that. Well, I mean, because it's a thing. Right, so argument expected str but got integer. Well, yeah, because you cannot have a value of string on the stack anyway, it's kind of pointless to forbid that, but I can do that anyway. Right, so though type check load pointer to type check store ptr2. Right, and then here we can do the same thing. Primitive, if the primitive is are they nearby? Can I just copy paste it from, yeah, I can copy paste it because it's easy. So even though this code is kind of unreachable, I just want to put this here just in case. Alright, so unknown word lock. Do we even have lock anywhere? Or do we have a token? I think I can use token lock pointer. Plus, again, this code is unreachable, but I just want to have that anyway. But it does Okay, so it does check this thing. So it is reachable. All right, whatever. So what if I try to do something like 10? Right, can I do 10? Incorrect field index. Okay, so that's fine. All right, so the basic structures do work. Right, the basic structures do work. So what do we need to do in here? We need to have named fields, right? So I want to be able to refer to these things by name. Here would be good to call it a count. Then allow structures within the structures. And also I need to think about dereferencing and referencing the structures as a whole. So I'm not really sure how to do that, and I'm not sure if it's really needed, right? Because you can kind of always do that without it. But again, the language isn't finished, so I'm not certain about anything. Right, so, but we do have a new toy in the language, and we may start migrating slowly the code base to like using this kind of thing, right? And of course there's all the friction on between these features and the intermediate representation, but we can now use these features to refactor the intermediate representation. You know what I'm talking about? So yeah, it should be easy. It would be kind of nice to like migrate all of these fields and whatnot, you know, the things that we introduced in here. Where is it? All of these things to use the actual structure, right? So they're implementing, make them implement the feature that they're implementing, right? So that would be kind of cool, kind of also convenient. Yeah, and also, but for this one, we'll have to have structures within the structures and whatnot. Yeah, that's pretty pogue, isn't it? I think it is. So yeah, so that's basically the design of the structures, like a rough sketch of the structures. I'm gonna be improving it and like, you know, fixing the rest of the to-dos and whatnot, but that's the basic idea behind all of that. So yeah, I guess that's it for the day. Thanks everyone who's watching right now. I really appreciate that. Have a good one, and I see you hopefully on the next recreational programming session. Stay safe. Love you all.